Okay, so let's take a look at another question. Here we want to determine the intramolecular forces found in CH2O, and CH2O is actually formaldehyde. So formaldehyde actually looks like this, right? And if you don't understand how we came up with that, we'll kind of do a step-by-step showing you the Lewis-dot structure. We'll generate the VSEPR and the electronegativity difference. Okay, so I'm just going to erase that so we can go through it. So let's look at the Lewis-dot structure first, like we usually do. So to do that, I'm going to just generate a chart here. I'm going to write down the three atoms that make this species up. There is the carbon, the hydrogen, and the oxygen. Carbon is going to have 4 valence electrons. Hydrogen will have 1 valence electron because there is 2 here. I'm going to multiply by 2. And oxygen should have 6 valence electrons, so it should look like that. I'm going to write down in this column here total number of electrons in the stable octet, which basically represents the total number of electrons you should have in the entirety of the molecule to make sure that each atom or element is satisfied. And we also have total number of valence electrons, or electrons that are found in the valence shell. So for carbon to have a stable octet, it should have 8 valence electrons. For hydrogen to have a stable octet, it should have 2 valence electrons. And for oxygen to have a stable octet, it should have 8 valence electrons. Now because there's 2 hydrogens, I'm going to multiply this by 2. And if we add up this to find the total, we should get 8 plus 4, which is 12, plus 8, which is 22. For the total number of valence electrons, you can notice this using the Lewis dot symbol that I've generated here. There's 4 valence electrons for carbon. There is 1 for each hydrogen, but because there's 2 hydrogens, I'm going to multiply by 2. And for oxygen, there is 6, right? So if we add up all of these in total, right, what we can notice here is that we have a total of 12. Okay. Let's see if the math here is right. So we had 16, 4, sorry, this should have been 20, guys. My mistake with the addition, whoops. I see everything is going wrong here. Okay, so that's 20, right? And what you could do prior to this, I know we showed an extra step in the previous video, but what you could do prior to this is look at your central atom, right? So your central atom, we'll call this step 2 actually, just to keep it consistent. The central atom here, out of these 3 atoms, well, 4 atoms in total because there's 2 hydrogens, the central atom here is carbon. Okay. Now based on this chart here, we can find the total number of bonds we should expect in our structure. It's basically the total number of electrons in the stable octet minus the total number of valence electrons divided by 2. So we get 20 minus 12 divided by 2, which should give us 8 over 2, which is 4. So we should expect 4 total bonds, right? And what we can do with this is we can pretend we could think about a potential arrangement of this, but we can imagine that, each hydrogen would have a single bond, and to accommodate for the other 2 bonds, we should have a double bond with oxygen, right? So this is a potential arrangement. So in step 5, let's look at our Lewis dot structure here, right? But our Lewis dot structure here, if we make carbon in navy blue, let's say has 4 valence electrons, well, it's going to have 1 valence with each hydrogen, whoops, and it's going to have a double bond. Sorry, my cursor kind of disappeared there, guys. It should have a double bond with the oxygen. So let's make hydrogens here, make hydrogen in dark red. And the oxygen, we'll use like a different color for this. Let's make this in light blue or baby blue. Looks like that. Okay, that's the Lewis dot structure. Right now you can see that oxygen has access to this. Each hydrogen has access to this, right? And the carbon itself should have access to all of these. So everything satisfies the octet rule, right? They all have a filled valence shell, right? Hydrogens don't necessarily have 8 valence electrons. They only need 2 to form a stable octet. Okay, so another way we can express this is we can also use the structural diagram, which we actually drew out here, right? The structural diagram, each pair of bonding electrons is basically a single bond, and 2 pairs of bonding electrons is a double bond, and 3 pairs forms a triple bond. Okay. So now that we have the structure out of the way, what we need to think about is our Lewis dot structure. Excuse me, we need to think about our VSEPR structure, our 3-dimensional structure. Okay, so VSEPR structures, it's going to be dependent, so I'll call this step 6, on the number of lone pairs on the central atom, the number of bonding atoms on the central atom, and the sum of these two will form the total number of electron groups that surrounds the central atom. And in this scenario, we have on the carbon, we have 0 lone pairs. We have 3 bonding atoms. So the total number of electron groups that surrounds the carbon should be 3. So this basically constitutes a trigonal, planar geometry as well as molecular shape, right? So essentially what our VSEPR structure should look like this. So that's how I actually generated the first diagram that I showed out, but right, in case you guys understood it, you could have skipped this portion of the video. Right, but this is essentially how you can generate that. Okay, now this is a trigonal planar structure, so this is 120 degrees. It's called trigonal planar because if you actually thought about a plane, sorry guys, I think I lost my cursor there. Right, if you thought about a plane here, right, or also known as a flat surface, and you had the atoms oriented in that plane, they would all lie on this same plane on that flat surface, and this be 120 degrees. Okay, so the next thing we need to do here, let's determine electronegativity differences. So for us to actually determine electronegativity differences, what we need to do is we need electronegativity values. So you guys would need a specialized table for that. That's usually given to you on assessments. The values I'm going to be giving you based on what I have in front of me. The electronegativity of oxygen is I have here 3.44. The electronegativity of carbon is 2.55. And the electronegativity of hydrogen we're going to be using is 2.20. Okay. So when we're assessing electronegativity differences, it's always between 2 atoms or elements. And essentially, the only 2 different types of bonds that you can see here is between the carbon and oxygen, and the carbon and the hydrogen. Let's start with the carbon and the oxygen. Okay, you can think about this as a double bond. The double bond, single bond nature won't really affect it, right? Because we're particularly looking at how the electrons are organized in this bond itself. So we're doing electronegativity of oxygen minus the electronegativity of carbon, which is basically 3.44 minus 2.55, right? If we calculate this, take out our calculator here. All right, you guys can probably do this in your head. This is 0.89. Okay, now our electronegativity interval table that that was the previous question. So our electronegativity interval table here, if it's greater than 0, less than or equal to 0.45, this is a nonpolar covalent bond. If the electronegativity difference is greater than 0.45 but less than 1.7, this is a polar covalent bond. And if the electronegativity is greater or equal to 1.7 but less than or equal to 4.2, this is an ionic bond. Now because we're looking at a molecular structure, these are the 2 intervals that are going to be relevant to us. In a nonpolar covalent bond, we have symmetrical or equal electron sharing. In a polar covalent bond, we have asymmetrical or unequal electron sharing. So in this scenario, we actually have the generation of a polar covalent bond, right? Then we can also assess the carbon and hydrogen. We do the same thing, except we're using the electronegativity values of carbon and hydrogen, which is basically 2.55 minus 2.20, which is 0.35, and this is basically non-polar covalent bond. Right? Whenever we have a polar covalent bond, we can also generate a dipole moment, which points to the more electronegative species. So it should look like that. Okay? So we can in fact here see that there's only one dipole moment created. That means that the net dipole moment on the molecule is not zero, which tells us that this molecule is polar. So it is in fact a dipole molecule. So it's a polar molecule. Okay, and because it's a polar molecule, guys, we can think about the intermolecular forces that are present here. All right, the intermolecular forces, there's line dispersion forces, there's dipole-dipole forces. Now, hydrogen bonding does not exist if there is cohesive forces. So cohesive forces means between the same molecules. They're forces or intermolecular forces between the same molecule. So what I mean by that is if you had two of these side by side, right? You can imagine that, you know, this portion here is partial positive, partial negative, partial negative, partial positive. Right? You can see that there is a force of attraction here is only between the carbon and oxygen. It's not between oxygen and hydrogen. So hydrogen bonding only occurs between hydrogen as well as the three most electronegative species or atoms, which include nitrogen, oxygen, fluorine. So there is no hydrogen bonding by itself, but it depends on what physical property we're looking at, right? If you did in fact see, if you were looking at solubility, for instance, between water, which we know is a polar molecule, right, and, you know, this species here, right? Like if we had a water molecule that was located here, let's draw it. So you can see this. Let me just erase some of this so we have some space. If there was a water molecule here, which we know is a polar molecule, right? There's a partial positive on this hydrogen here. You can imagine there is asymmetrical electron distribution due to the electronegativity differences. You notice that this partial positive and this negative here, there would be, whoops, let's get rid of that. There would be a hydrogen bond between this oxygen and hydrogen. Okay, so it really depends on which physical property we're looking at, guys. But if we're looking at just the intermolecular forces of the same molecules, cohesive forces, then there is no hydrogen bonding. But if we're looking at adhesive forces, like between formaldehyde and water, then there could be the presence of hydrogen bonds. So you have to be very careful on what physical property you're looking at. But in general, these are the intermolecular forces you would find between these molecules, the same molecules. Okay, so keep that in mind, and that's the whole idea. Now, if there's anything you didn't understand in this video, I'm going to tag the full overview of VSEPR structures. That's also going to kind of highlight some Lewis dot structure knowledge as well, but also it will go through the different types of intermolecular forces in detail. It'll give you a definition of each of them. And also some sample questions. So I'll tag that video in. It's a pretty long video. You don't have to go through the entire thing, guys, unless you want to. If you really need a thorough explanation of it, you can pick and choose certain aspects, but you can also use that as a reference. Okay, so thanks for watching. Congratulations on finishing the video. To reward your attention and determination to learn and enhance your skills, we've created a new reward system this year. Each time you complete a video, you will be rewarded IQ points. Depending on the length, difficulty, and type of video, instructional versus question-based or both, you can be rewarded different levels of IQ points. These IQ point rewards will be either 10, 20, 50, or 100 points. Our goal for implementing this system is to enhance your motivation and improve your daily productivity. Use the amount of IQ points you earn each day to reinforce and gauge your commitment towards your education. And while you do this, remember to like, comment, subscribe, and share our videos. Your continued support will assist us to release more free educational content in the future. Our collective goal at Course Concepts is to assist you towards academic success, one step at a time, because success starts with a single concept. So we want to thank you for being a member of Course Concepts.